Okay, so this morning, we will conclude our discussion of tired of Ministry of Education saying that we should stay home. Well, yes, we will. This morning, this is the fourth sort of lecture on oscillators, and we will conclude the topic this morning. Finishing off some discussions on the RC networks. Some discussions on crystal oscillators, which are going to meet in microprocessors, not directly in this form, but you use them. And then a little discussion on stabilizing the oscillators themselves. Okay, so as usual, if you have any questions, feel free to interrupt, ask a question, and try to get my attention, and we will answer it as we go along. Right, so again, keep reminding ourselves of the conditions for oscillation. Remember, the oscillator is a feedback network. It is a positive feedback circuit or network that we have. And what we do is that we have a feedback network that we identify here as beta, and we have to make it in such a way that the gain the loop gain is 1, and that the total phase shift is 0 or multiples of pi. That is how we get the positive feedback and the positive reinforcement, so that basically once the system starts, you don't need that Xi input. The system will continue to oscillate for itself. And the theory, system theory, is that systems of this nature, once they start to oscillate, the frequency of oscillation or the signal of oscillation is a sinusoid. It has a particular frequency, so it doesn't produce a square wave or a triangular wave or the like. It's fairly easy to do, and you will prove that in your controls. But the thing is that in a system like this, the natural frequency of the positive feedback, once it starts to resonate or to oscillate, is in fact a sinusoid. You can't get another sort of waveform coming up. If you're not careful, sinusoid, which is what happens when the amplitude goes out of whack, and we'll talk about that towards the end of the topic itself. All right. And last time we spoke about this particular design, which was one of the phase shift oscillator designs. And once you, what we said last time is that with the phase shift of oscillator, the sections are RC sections. You can have an RC lag or an RC lead, depending on how you, which of the components is tied to ground, either the C or the R. But they interfere with each other. If you don't have the op-amps, each section sort of interferes with the other one. So you have to work out the overall transfer function. And we saw that it's a sort of ladder divider network. So it takes a little bit of arithmetic to get the final, what do you call it, transfer function down. This approach is a little bit easier in that you separate each section with a unity gain buffer. And remember, the unity gain buffer, the voltage follower, has a high input impedance so that it doesn't load the RC network. And remember, loading, Dr. Radek sort of briefly mentioned it yesterday. Loading has to do with the current or the voltage that you're asking something to provide. A simple RC network, if you put another, what do you call it, the time, let me get my pen here. From the time you take this and you add, you put something else onto it, this now has an impedance of some sort going in. So that impedance now appears with this one, and therefore the overall behavior of the RC network changes. So when we had the three of them cascaded with all the op-amps, if they were all cascaded, then each RC section basically loaded the previous one, which is why, as we said, the arithmetic or the algebra got a little bit complex. By putting the op-amps here and making use of the fact that the unity gain op-amp or the voltage follower has a very high input impedance, each state is basically separated from the other one. The op-amps take little to no current going in. The ideal op-amp doesn't take any. Of course, we know that's impossible, but it takes a very, very small amount, a minuscule amount, typically in the microampere range, so that each section is separated from the other one. And we worked out that one, so it was basically transfer function of that cubed. And from that, we were able to get the natural frequency either in radians or in hertz. And then once we did that, you plug the natural frequency or the resonant frequency back into the transfer function, and you see what the gain of the feedback network is. And therefore, if the gain of A beta has to be equal to 1, then if you know what the gain of this part is, then you could figure out what the gain of the amplifier is. As it turned out, the gain of the amplifier had to be, anybody remember from last time? Is it 1/3? Think about it. Okay, there's a hint on the diagram up there. Look at RA and 8RA. What kind of amplifier we have there? What kind of amplifier do I have here? Right, inverting. Right, so if I have an inverting amplifier, and what's the gain of that amplifier? What's the gain of the amplifier? -8, right? It's an inverted amplifier, so the gain is -8, right? So that's in order for this to work. Therefore, the amplifier, you have to have a gain of -8. The gain of the 3 was to do with the Weinberg oscillator, which was the earlier one that we did. The network had an overall gain of 1/3, so the amplifier had to have a gain of 3, right? So that's the process. So you look at it, you analyze it, and from you get the gain of the network, and then in order to make it 1, of course, you have to have the amplifier accordingly, set accordingly, right? So here's a variation of this one. So if I were to give you this now and ask you, well, analyze this. By the way, this is called a multi-phase sinusoidal oscillator. It is using 3 identical sections here. You can see them, 3. So 1, 2, 3. They're all identical, and they are supposed to give us the 360 shift around the loop. So each of them is giving me a 120-degree output. So V1, the phase shift between V1 and V2 is 120 degrees, between V2 and V3 is 120, and between V3 and V1 is 120. So in fact, this kind of thing is giving us a 3-phase output. It's a kind of circuit that you can use if you want with some power electronics, which are high voltage and high current electronics. You can use this to create a 3-phase, a small 3-phase power supply, an AC 3-phase power supply. So if you were to make this, let's say, a 60 hertz oscillator, you would get 60 hertz voltages coming out, well, whatever is the amplitude of the power supply here, coming out low current, of course, but they would be spaced 120 degrees apart. And then you supply that now to high power electronic circuits, and you have now the ability to drive up a high current, high voltage load for a small period, for a small time. So the kind of the the kind of thing that you can see an application in power electronics with. So if I were to ask you now, okay, how would you go about analyzing the following? Step one would be what? What we've done before. So this is kind of, half review, half looking at how you approach the things. 3 identical sections. So what's the first thing to try to do? Anybody? Suggestions? Let me know every so often if you're hearing me, by the way. Hearing me? Good. So hearing, but like Dr. Alex, and ask you all to put up faces and all that kind of thing. Yeah. Knowing where to start, right? Okay, well, like anything, you start with what you know. So already it's 3 identical sections. So we start with 1. Let's look at this section. Right? So forget everything else. So we have something here. We have an amplifier, and on the inverting side, it looks like an ordinary inverting amplifier, except that we have a capacitor in parallel with a resistor. So remember, this is the oscillator. So we're looking, there's a feedback network and there's an amplification. There's amplification and feedback supposed to be taking place inside of here. So you break it down, and let's look at one section and see where to go from there. So if you look at that particular section, what is the transfer function of that section? Think of it, again, think of it like so we have an inverting amplifier. We have 2 impedances here, right? So the amplifier, you have this. This is Z1, let's say this is Z2. Okay, so if I were to give you that and tell you no information, what is the input-output relationship of that? It's an inverting amplifier, so that the input-output relationship for that is what? Right, it will be minus Z2 over Z1, right? Good, so treat it like that. So minus Z2 over Z1. And now Z1 is R and Z2 is what? Z1 is R and Z2 is what? Z2 is equal to what? Right, R in parallel with C, right? Good, XC in parallel with R, or if you want in the Laplace domain, right, R in parallel with 1 over SC. Right, so if Z2 is R in parallel with 1 over SC, it will be what? R over R plus 1 over SC, etc. R over SC over R plus 1 over SC, and you simplify it. Your normal little basic circuit theory now. So you work out that, and you get that the first crack here now is that, right, that the transfer function for that section using the same little thing is minus R over R1 over 1 plus SCR. Yeah? Everybody following? If you're not following, just let me know, right? Remember this circuit here, that part, one section is just an inverting amplifier, but the feedback part of the inverting amplifier is an impedance. So the transfer function, the normal transfer function for that will be minus Z, if I call this according to what I have, 1 over R1, and Z1 happens to be C in parallel with R, which will be R over SC over R plus 1 over SC. And if you multiply it all through, right, you will get R over R plus SCR, right, which is what I have up here. Yeah. So you get this bit. Right, let me just, some strange reason, right? So you get this bit here, and then we multiply it up by the other part, which is, or divided by R1. So there you go. Make sense now, Joshua? Right? So, and what is the transfer function of all three sections, therefore? Right? Remember we did that. So if this transfer function is, just for argument's sake, let's use some of the terminology that we know to use. So this transfer function is G1S. This transfer function is G2S. And this one is G3S. From yesterday, we know that there's a cascade kind of thing. So the overall transfer function is this by this. G1 by G2 by G2. And if each of them has the transfer function of this, then the overall transfer function is what we have there cubed. Yeah? Yeah, no, maybe. That part is easy. Right. So what is omega 0? So if I ask you that now, what do you have to do to find omega 0? The resonant frequency of that particular oscillator. What's the next step? You're given the transfer function, and now you want to find the resonant frequency. So what's the next step that we have to do? We did this way back even with the Weinberg, which is where we started off, and so on. You have to make a substitution now, which is what? What's the substitution? Something equals something. Not yet, Jared. We have to get to that position. No, not yet. 2 pi f meaning what? What am I substituting 2 pi f? Right. Very good, Zedan. We have to substitute S equal J omega. Right. So we have to substitute for S here equal to J omega. And then simplify. All right. So, and what is and after we do that, of course, we are required to satisfy what? For this thing to work, we have to satisfy something. Right, that's the mathematical part, but the criterion is again back. Right, we have to satisfy the Barkhausen criterion. Right, so we substitute S equal to j omega inside of there. Correct, as Zenan pointed out. And then we expand it. And then we have to make, because of the Barkhausen criterion, the phase shift has to be either 0 or multiples of 2 pi. So in order for that to happen, the imaginary part of whatever we do on top there is supposed to be 0. So take a couple of minutes now, and I want you all, I mean, this will be half revision and half trying to see how the thing works instead of me just giving the answer. Substitute S equal to j omega in that transfer function above there, right? You could probably use, just to simplify it down, I think in the notes they said k equal to minus r over r1, right? So that transfer function is really minus k over 1 plus src all cubed. So if you make that substitution inside of there, substitute S equal to j omega, and take a couple of minutes and tell me if you could give me an idea of what omega 0 is going to be. Right, so you have is 10:28. Let's see if you could do a little bit. It shouldn't take you more than about 3 minutes. So at 10:31, I will like to see some answers coming up. Something. Give me an answer. And yes, you could call up each other if it's anything. Well, one because when you solve it, you're dealing with, when you substitute for j equal to, sorry, s equal to j omega in here, will get an omega cubed in here. One of the answers will be that omega rc is 0, but that's not practical because 0 omega rc being 0 means that omega is 0. So that's a non-answer, right? You remember we did that for the phase lead and phase lag networks, and you're going to get, because it's omega cubed somewhere inside of there, that you're going to get one answer is 0, one answer is negative, and then one answer is positive, right? Because it's a cubic polynomial that you're solving. Okay, I'll give you one more minute. We are 10:51 now. Right, so anybody close to an answer? Almost. Okay, 1 minute. Right, so what sort of answers we got? Omega equal to what? Right, we got 0 before, which is a non-answer. And we're supposed to get plus or minus something, the positive part of the answer. Okay, anybody? Okay, so we have a plus or minus root 3. Yeah, but it must have R and C in it somewhere. Right. Anybody else got an answer looking like that? That omega naught, well, you discard this one and you discard this one. Omega naught is root 3 over RC. Anybody else got that? Which is correct. What did you get, Jared? Still trying to. Okay, so don't let the working confuse you, right? When you substitute inside of here, the best thing to do is that once you're given the transfer function like we have here, once you're given this, right, you have to substitute S equal to RC, sorry, S equal to j omega inside of here. What I would suggest is that you expand this first. So you get a polynomial and you'll get a polynomial in S cubed, S squared, S, right? Then you make the substitution inside of there. So when you get S, when you substitute the S equal to j omega inside of here, this one is going to give you a minus omega cubed. This one is going to give you a plus omega squared. Stuck with a j omega, right? So then you group the imaginary and the real parts together and you solve. And you see what, sorry, this is going to give me a j here, right? Because j cubed is minus j. Right, so you're going to get a minus j omega cubed. The S squared will be just omega squared. The S going to give me a j omega. So you group the parts with the j's together and the parts, the real parts and the imaginary parts. And as we said, to satisfy the Barkhausen criterion, the phase angle of that thing has to be 0. The way that the phase angle will be 0 is if the imaginary part is a complex number. So if the imaginary part is 0, then we only have a real component. So therefore, the phase angle is 0. So you set that equal to 0 and you solve. And because it's a cubic, you're going to get 3 answers. One, which is in fact 2 answers, which are non-answers. One is that omega is 0, yeah, okay. And the other one, which is a plus or minus square root. And of course, we take the positive square root answer for it. And then that's part 1. And then the part 2 now is that what is the overall gain? And that's where our I comes in here. So after you finish that inside of here, then you plug omega 0 equal to this value back into the transfer function that you had when you substituted for S, right? You know the imaginary part is 0, so you could ignore that and just look at the real part. And if you substitute the omega, then you will get that the gain of the amplifier, the overall gain of this is supposed to be 8. So each section, therefore, if it's 8 and it's 3 sections, remember it's a G1 by G2 by G3, each individual section has to have a gain of 2. So 2 by 2 by 2 will give it 8. Yeah, because the overall gain of the feedback network is 1 over 8. All right. So this again is a little bit of analysis. The reading for this is actually in the handout that I had put up on oscillators. It's somewhere in the middle there, the multiphase sinusoidal oscillator. But it's always good, because I've seen some typographical errors in the notes as well, but it's always good to be able to know how to work it out. And as we said, you just watch the circuit. If you watch the circuit carefully, just look at it. This circuit, 3 identical parts, and each part is really an inverter, but one of the feedback element on the inverting amplifier is an impedance, is a parallel RC network. And you just go step by step. You solve for one, and then it's one by the other, and then you make your substitution. Yeah? Just like we did for the previous case. Once the op amps are in the middle buffering like this, and in the previous, the phase lead with the buffered amplifiers in there, it's the analysis is very straightforward. The other one with the lead lag network is a little more complex, because the ladders divide and feed each other. All right? So everybody all right with that? Yeah? Kind of did a halfway revision in a way, so it forced you to think a little bit instead of just accepting the notes as is. And once you do this, so you have the transfer function here, omega 0. I didn't put it on the slides, but you know omega 0 is √3 over RC, and the gain of the whole thing is 8. So each section has to have a gain of 2. Okay? So any questions? All right. Okay. So take a 2-minute break, because we're going to talk about crystal oscillators next. So I'll break up the sessions into that, and then the last session we're going to talk about is a little bit of amplitude stabilization. Right. So stop this part here.